part 2 of this chapter, Introduction to Graphing, we will learn how to set up a function/equation. So you're going to be given a word problem, and you have to turn that word problem into a function and then later solve certain questions from it. So let's get started. So for example 1, the computer purchased in 2015 has an initial value of $1,500. The computer depreciates at $150 per year. Write a function in x that represents the depreciation in value. Then we want to know what the value of the computer is after 5 years. So to start off with, read this example one more time. Think of how you would set up what's happening here. You're making the function, given the information. So pause this video, read it one more time, set up your function/equation, and then we'll go at it together. Alright, so there's some key words here. Originally it was, or initially, the value of the computer was $1,500, so that's needed. And then it tells you it's depreciating at $150 per year. So depreciation means it's losing that value. So at least you still had to pay the $1,500 up front, but then it loses $150 every year. So X is representing the years. Right? And so many of you may have it as this, which is okay. Y equals all of that. But you remember, we're swapping out those Y's these days for f of x. So the second one here would be a little bit better notation. Swapping out the Y's with the f of x. Okay. Let me erase this because I've actually included it in this slide to where it will pop up. Okay. And so now the question is, how much would the value of the computer be after 5 years? So part 2 of this, after 5 years, how much is the computer? Well, 5 years is your x. That is your input value. That is your independent variable. That when you plug it in to your x, you are going to get your outputs, or your dependent variable. Take a minute to solve that and see how much the computer will be after 5 years. Okay, should be $750. So you plug the 5 in there, 5 times that 150, minus that from the 1,500, you get $750. Okay, so let's bring up same example, but now it's asking for the domain. So it's kind of bringing up what you had in part 1, reminding us domain. So we still have our function to where it's depreciating at $150 per year. But now thinking of the domain. Domain meaning all of your x's, all of your real x's. So if you remember back in part 1, it made the comment that they wanted real values for x's that would give you real values for your y's. So what did all that mean? That's when it comes into terms of the example. So think of some x's that would work here. We've already seen what happens in 5 years. Maybe see what happens in 1 year, or after 3 years, or 7 years. Kind of play around with the different amount of years to see what happens to the value of the computer. If you'd like to make a table, go ahead and do so. X is what you're plugging in. So if no years have passed, 0 time has passed, how much was that computer? 1,500. We saw after 5 years, it was 750. Think if there's ever a time, ever a year, amount of years that have gone by, to where this equation, this function, wouldn't really make sense to us. Pause this video and think about that. Try some different years in it. Maybe 20 years, 50 years, 60 years. Try all of those. All right, so the certain year I was looking for is 10 years. What happens after 10 years? If I plug that 10 into your function, what did you get for the value of the computer? Should have been $0. So where the computer would be worthless after 10 years. So that's what we mean by the domain. The domain will be from 0 to 10 years. Or in other words, 0 to 10 years. If we want to use our inequalities, x, there's my 10, x has to be greater than or equal to 0. It can't be a negative year. You're not going back in time. But then x cannot be greater than 10. Because once you hit 11 years, what happened to the value of the computer? You end up in the negatives. It doesn't really make sense for our real world example for this. So that's what it means by the real x's that would work in this case to make sense for our dependence. So what that's telling me, 0 years, 1 year, 2 years, 5 years, 7 years, 8 years, all the way up to 10 years are my possible domains, possible x's, possible inputs even, if you want to call it that way. Okay. What about the range? So once again, you have that same function, but now we're looking for the range. So the range was the y values, your dependent values. So in other words, what happens when I plug in those x's to get those domains? Well, we saw already that our domain, put that one up there again, was between 0 and 10 years. So thinking about our range, those are going to be our y values. And for our y values in this case, we're talking about money. So dollars. Y is our dollars in this case. So if no years have passed, how much was that computer worth initially? $1,500. Could this computer ever be worth more than $1,500? Keep in mind, you're not adding anything extra to it. You're not vamping it up. So you're not going to turn around and sell it for more than you paid for it. It's just a straight computer, flat computer, standard. So you can't go over that $15,000, but you could go right up to it. We also saw after 5 years, Y could have been $750. What was the lowest amount of price this computer could be? $0. Because you remember, after 10 years, the computer is worthless. So for your range, you're talking about the dollars here, the money, the total cost of that computer, and it varies between anywhere from $0 to being worth $1,500. All right. Okay. Now, take a minute to graph the relationship between the price and the time. So pause this video for 1 second and graph. Okay. So your graph should look something like this. You're dealing with time and years down here. You're dealing with cost over here. Anywhere from 0 to 10 years. It's going all the way up to 1,500. And I'm being pretty quick with my graph here. You can always work on it a little bit more detailed. Like if you want to say 1, 2, 3, 4, and onwards, that's up to you. So if 0 time has passed, I'm here, I'm right there. 0 time has passed, how much was that computer worth? $1,500. After 5 years have passed, how much was it worth? $750. And then after 10 years, the computer was worth $0. So that's what we mean by a linear function. It's a nice straight line. There's a constant slope to it. It could be increasing, it could be decreasing. This one's decreasing because it's depreciating, but either or. All right, example 2. Read over it, pause this video in just a second. Okay, pause this video and try A, B, and C. given the following word problem. Okay, so welcome back. I hope we've looked at a function that represents the relationship between the number of t-shirts to the total cost. I was looking for f of x equaling 200 plus 12x. So 200 was that flat rate. You had to pay the 200 setup fee regardless, and the $12 was for every shirt. So x is representing what? The number of shirts. Alright, so for b, determine the domain and range of your function. Your domain are your x's. So in this case, it's the number of shirts. Well, is there a limit to how many shirts the club or the team could buy? It doesn't say anything about being only 50 people in the group or 60 people in the group. It doesn't tell you where that cutoff is, unlike the computer one. So for your domain, you could order 0 shirts and still have to pay the 200, or you could buy 1 shirt, 2 shirt, 5 shirt, 50 shirts, 60 shirts, and so on. So anything greater than that 0. Greater than the 0, because would it make sense to have any negative numbers, negative shirts? No. So that's where it goes back into that real world, does this X work, is it reasonable, that kind of thing for your domain. So we want things that work for our situation. Now for your range, so range are your Y's. So in this case, the Y is representing the total cost, or also known as our f of x. It's representing the cost in dollars. So what is the very minimum you're going to have to pay for these shirts? It'd have to be 200, wouldn't it? Because even if you buy no shirts, let's say we have bought no shirts, so we say 0 for our X, you still have to pay the $200 as the startup fee. But then anything greater than that works as well, because maybe they buy 1 shirt, so now it's 200 plus 12. They buy 2 shirts, 200 plus 24. And it goes up and up and up, but it at least starts at 200, even if they buy no shirts at all. Take a second to graph your function. I don't have much room here to graph it, but you have your number of shirts down here. You have your total cost over there. So even if you bought 0 shirts, you still have to pay $200. Let's say they bought 10 shirts. Then you're paying $320. So you can see how this one's going to keep climbing, and I'm going to put an arrow at the end because there's never a cutoff. There's never a thing that tells you how many shirts you have to stop at. You could just keep buying shirts all day long. So it's still linear and it's increasing. And we put the arrow on the end because it continues to go higher and higher with the cost. Now realistically, you wouldn't buy 1,000 shirts, but they still could. There was nothing in the problem telling me I couldn't. So that's what we're looking for with our domain and our range. That real value of X or the real value of our Y. Alright, you guys will have a worksheet on setting up your equation. So try out that worksheet, but always come back to this slides, this video, to see how to set them up. It's a little tricky sometimes.